Okay, here I will show how can we determine the string or the string status at a point in a real-world structural member. Okay, you know that stress is a mathematical abstraction, so it actually cannot be measured directly. You may be able to measure the loading, and if you know the dimensions, you can calculate the areas and calculate the normal stresses in some way. But normally you cannot measure the stress directly. But strains, on the other hand, can be measured directly through well-established experimental procedures using the correct equipment. For example, here, what is shown here, this is a tool that is regularly used in engineering to measure the strain, which is called strain gauge. Okay, this is a strain gauge. It can just measure the linear strain values at a point where it's attached. So once the strain in a component have been measured, the corresponding stresses can be calculated from stress-strain correlations, such as the Hooke's law. Okay, in next lecture, we will derive the generalized Hooke's law. Using the Hooke's law, you will be able to calculate the stresses based on strains in a structural member. Okay. So what is shown in this slide are some examples. You can see the structural members. Where it says the strain gauges can be attached on the structural members to measure the linear strain values at a point. Okay, or it can be embedded in some structures like a concrete pavement to measure the local strain values. But the question is, a strain gauge can only measure a normal strain in a specific direction. But at a point, to determine the stress, the strain status, you need three components, by three quantities, say epsilon x, epsilon y, and gamma xy. But how can you determine three quantities by using one component that measures normal strain in only one single direction? The answer is no, you cannot. Okay, the answer is you have to use multiple strain gauges. Okay, if you have several strain gauges and you can arrange them in pre-designed directions, then based on the values you read, then you can calculate the strain values along x and y directions and calculate the shear strain. Okay, so this method is called strain rosette. Now you can see here, these slides demonstrated how can you use multiple strain gauges to determine epsilon x, epsilon y, and gamma xy. Okay, the strain rosette equation is shown here. Okay, this is actually the same equation as the strain transformation equation we used in the previous example. Okay, these two equations are the same. They are the same equation, just in different mathematical forms. Okay, you can try to derive the strain rosette equation from this strain transformation equation by yourself. Okay, you can try to do this equation transformation. Okay, so the strain rosette method says that if we can use three strain gauges and set them with known angles to the x direction, we will get three equations. Okay, these three equations just have different theta values. Okay, one example is shown here. So you can see that these are the predetermined. You can assume the directions x and y in a structural member. That you attach three strain gauges with different angles to x-axis. Gauge A with theta A, gauge B with theta B, and gauge C with theta C. Okay, based on this setup, then when you load it, you will be able to get three readings from the three gauges A, B, C. Then you get epsilon A, epsilon B, and epsilon C. Okay, based on this equation, based on the strain rosette equation, or the strain transformation equation. Actually, what you are doing is strain transformation. Okay, you can also use this equation, but the calculations will be more difficult. Okay, the string row set equation is much simpler. Okay, so normally we just use this equation, okay, to achieve the same purpose, that is string transformation. Okay, you just correlate the epsilon x, epsilon y, and epsilon and gamma xy to the readings, to the three readings, epsilon a, epsilon b, and epsilon c, with this equation. Okay, you will get three equations as shown here. Well, in these three equations, epsilon x, epsilon y, and gamma xy, these three things, three quantities are unknowns. But the epsilon a, epsilon b, epsilon c are known. They are just the readings of the three string gauges. Okay, so three equations, only three unknowns. So you can solve them mathematically simultaneously. Okay, so after solving this equation, you will get epsilon x, epsilon y, and gamma xy. If you still want to know the outer plane string, like epsilon z, you can use this equation. Okay, this equation can be used to calculate epsilon z, that is called out of plane string, from epsilon x and epsilon y, as well as the Poisson's ratio. Let's see a example directly. Okay, here the string row set consisting of three gauges, string gauges, oriented as shown here, mounted on a free surface of a steel machine component. The steel has a Poisson ratio 0.3. Under loads, the following strain were measured. Then determine the principal strains and maximum shear strain at the point. Show the principal strain deformations and the maximum in-plane shear strain distortions in the sketch. Okay. Here the three readings have been given. These are the epsilon A, that is negative 600, epsilon B, negative 900, and epsilon C is 700 microstrain. And their angles are respectively theta A equals 0 degree, right? It's just on the x-axis. And theta B is 135 degree. And theta C is 225 degree, or negative 135 degree. Okay. So based on the string row set equation, we can write three equations. So the three equations are the first one, epsilon A, right? Epsilon A, that is negative 600, equals epsilon x cosine square theta A, that is 0 degree, right? Plus epsilon y sine square theta A, 0 degree, and plus gamma xy sine 0 degree cosine 0 degree. So in this equation, you can see that here you got a 0, here you got a 0, so here you have 1, right? So you can directly get that this is the equation 1, epsilon x equals negative 600 microstrain. Okay, then the second equation, just start from epsilon b, that is negative 900, equals epsilon x cosine square 135 degree, plus epsilon y sine square 135 degree plus gamma xy sine 135 cosine 135. This is our equation 2. Then the third equation, positive 700 equals epsilon x cosine square 225 plus epsilon y sine square 225 degree plus gamma xy sine 225 cosine 225. This is our equation 3. Okay, equation 1 has been solved. Right, it's from equation 2. From equation 2, you will get negative 900 equals since epsilon x has been solved, right, I will directly use it. Negative 600 times 1/2 plus epsilon y times 1/2, then minus gamma xy times 1/2. Okay. And from equation 3, you will get positive 700 equals negative 600 times 1/2 plus epsilon y times 1/2 plus gamma xy times 1/2. Okay, this can be further shortened into negative 600 equals 0.5 epsilon y minus 0.5 gamma xy, and 1000 equals 0.5 epsilon y plus 0.5 gamma xy. Okay, so it's easy to just add these two equations together. You will get 400 equals epsilon y. Right? So that is epsilon y equals 400 microstrain. Then you can also solve that gamma xy equals 1600 microradian. Okay, we just solved the 3 components based on this ring rosette. Okay. So after that, let's determine the principal strains and maximum shear strain. Okay, this is the next step. Here, so first of all, let's list these values. List the values here. We have the epsilon x is negative 600, epsilon y 400, gamma xy 1600 microradian. Okay, just from these 3 components, we can calculate the principal strings. They are just, we use the equations, right? Plus or minus the R value. R value here is sigma x, epsilon x minus epsilon y over 2 square plus gamma xy over 2 square. Okay, they will have negative 600 plus 400 over 2 plus or minus, in here you have a negative 600 minus 400 over 2 square plus 1600 over 2 square. Then here you will have negative 100. Here is 943. Okay, so you will get these two principal string values, positive 843 microstring or negative 1043 microstring, right? So these are the two principal string values. Then we can calculate the gamma max over 2. Okay, we have that equation too. We actually have determined that. Okay, so who can tell me the value directly? It's right in the previous, in the above calculations here. Okay, which number is the value of gamma max over 2? Here, right? So it's just positive or negative 943. So gamma max equals 2 times of that, right? It's 1887. Okay. So more strictly speaking, if you count in the number here after it, it's 0.4, you get a 1887 or 1884. Okay, this is just a small errors. Then we can also calculate so here, okay, what do we determine the gamma max is actually the in plane. This is the maximum in plane shear strain, right? Then we can also calculate the theta p as well as theta s, right? So we can, as what we did for the example 1. Okay, the theta p tangent 2 times theta p. 2 times theta p equals gamma xy over epsilon x minus epsilon y. Okay, no over 2. Okay, here is the strain, not stress, so no over 2. This is the equation. Then 1600 over negative 600 minus 400. You get negative 1.6. Okay, so here you can solve it. 2 theta p equals negative 58 degree. So theta p is negative 29 degree. So what is theta s? Right. Theta p is the angle you need to rotate to find the principal strain plane. Right. So how about theta s? That is the angle of rotation, the angle you need to rotate to find the maximum shear strain. Okay. So that is just negative 29 degree plus or minus 45 degree. Okay, as we included another equation in the previous slides, we can also calculate the out of plane strain. The out of plane strain out of plane, you'll be able to find another the third principal stress. That is epsilon P3, the other principal strain, the epsilon P3. Okay, that is the epsilon Z is negative. The equation said negative Poisson ratio over 1 plus Poisson ratio times epsilon X plus epsilon Y. Okay, the Poisson ratio is 0.3. Right, so that we get 0.3 over 1 minus 0.3, negative 600 plus 400. So you get 85.7. Okay, obviously this is a number between epsilon P1 and epsilon P2. Okay, so it's not critical. Okay, the maximum in plane shear strain has been determined. So now let's discuss what is the absolute maximum shear strain. Okay, to do that, we need to compare the three principal strains. You can see the values are listed there. So you will have epsilon P2 is the negative 1043 microstrain. It's the smallest one. It's smaller than epsilon P3. And the epsilon P1 is the biggest one. Right? That is 843 microstrain. Okay, so actually the P3 is not critical. We just need to use the P1 and the P2 to calculate the absolute maximum shear strain. So the maximum shear strain absolute equals. Now you just need to use the principles we talked about. Look at the signs of them. P1 and P2, they have different signs, right? They have different signs. So the equation said half of the gamma max equals epsilon P1 minus epsilon P2 over 2. Okay, so in that way, the gamma max absolute equals epsilon P1 minus epsilon P2. Okay, you get the result. That would be 843 minus negative 1043. So you will get 1883. Okay, microradian. Okay, you can see that this number is the same as here. Okay, the same as here. If you ignore this, here will be 6.2. Okay, you get the same result as here. Okay. So this again verified our theory, our principles. If you have different signs, the absolute maximum shear strain is the same as the in-plane maximum shear strain. Okay, so in the end, let's sketch them. Let's sketch the stress situations here. Okay, as what we did in the previous example, we start from a square. Here is x, y. And then from here, from the original status where you have epsilon x, epsilon y, and gamma xy, then how can you get the plane, the principal strains? The principal strains, you need to use this angle determined here. Let's use red color. Okay, the angle is here. They just rotate it. Rotate it in this way. You get an element like this. Okay. So here, this angle, theta p, right, equals negative 29 degree. Okay, you just rotate it clockwise. Then here you have negative 1043 microstrain, and then along the other direction you have a positive 843 microstrain. Okay, then how about the maximum shear stress? But as we just derived here, let's use green color. As we denoted here, the angle theta s will be negative 29 plus or minus 45 degree. Right? So you'll be able to find this position from here. Okay, you should be able to determine the angles. Okay, you can determine the angles by yourself. But here I just ask you one question. Right, what is the angle here? What is the value of this angle here? It's smaller than pi over 2, so its value should be pi over 2 minus 1886 microradian. Right? So this is a sketch of the principal strains and the maximum shear strain. Okay, so after that, the last slides just summarizes the method of the strain rosette. The solving the strain rosette problems, you have 3 steps. The first step, determine the strain values and the angle of each gauge from the arbitrary x-axis. Then in step 2, put the strain readings and angles in the following equation. As I mentioned, you can also use the other form of it, that is the strain transformation equation, but the calculations will be very complicated. You will not want to use it. So this form is much easier. Okay, the last step, you just solve the equation group to find out the three quantities you need to define the string status at the point. Those are epsilon x, epsilon y, and gamma xy.